All right, so in this particular video, we are going to start with a review of general chemistry. So in organic chemistry, there are pieces of Gen Chem that are really handy for us to sort of lean back on and make sense out of some of the reactions we're going to do here. And to start, this will just be a piece of chapter 1 where we're just going to revisit the electronic structure of an atom. I think the easiest way to do this, and just sort of like the clearest way, would be to focus on the shell model. And so depending on what kind of a Gen Chem course you took, you may or may not have heard of the shell model. It's basically just a cartoon version of an atom. It works really well for things like ionization energy or sort of like identifying the different energy levels, but it kind of stinks with sub-level divisions because it makes it look like all of the electrons in a particular energy level are degenerate, meaning they all have the same potential energy, and we kind of remember from Gen Chem that they don't. The shell model includes 3 sort of basic things. The nucleus, and so that's going to be our protons and our neutrons, but in the shell model, we don't draw the neutrons in. So we're really just sort of focusing on the nuclear charge. And the neutrons are sort of just implied. The other thing that we look at are the different energy levels. So our N levels. And we're going to call these the shells. Now, you probably also remember from Gen Chem that we have L values, right? Our quantum numbers describe the orbitals, and the L values are going to basically describe the shape. But in the shell model, we're only looking at the different energy levels. So these are going to be our little rings basically around the nucleus. And then in these energy levels, we're going to have our electrons. And these are just going to be hanging out in the various energy levels. And so these are just going to be little rings around the nucleus at various distances. So for example, the easiest one that we can draw obviously will be hydrogen with 1 proton. It has a nuclear charge of +1, and it has 1 electron in the N equals 1 energy level. So the thing about the shell model that's really nice is it gives you kind of a clear picture of the valence electrons for main group elements. So for hydrogen, obviously there's just 1 electron, 1 proton. We have 1 valence electron, right? So that's pretty simple. So this is just for hydrogen. One thing that you probably could think about, even just with simple little hydrogen, is the effective nuclear charge. So these are going to sort of go along with that trends in the periodic table that you probably talked about in Gen Chem. The effective nuclear charge is basically like, say you were going to interview that electron and ask it, hey, what's the charge in the nucleus? And the charge that it would report back to you in that interview would be for hydrogen +1. But what does that even mean? So in some Gen Chem classes, they call this the effective nuclear charge. Some Gen Chem classes call this the core charge. Trends that we noticed in the periodic table are that for main group elements, this effective nuclear charge, or whatever charge is felt by those outermost electrons, those are the valence electrons, by the way, is going to be equal to the charge in the nucleus, so your nuclear charge, minus any of the core electrons. Or some groups will call them shielding electrons. So in terms of hydrogen, there's only one electron, and there's no core electrons, no electrons that are in a shell closer to the nucleus, that is. So for hydrogen, we have +1 minus 0 is going to give us a +1 effective nuclear charge. So that's pretty simple, right? Just for hydrogen. But what if we move on to something like lithium? There are 3 protons in the nucleus. For lithium, if you're looking on the periodic table, you'll see that it's in the second period, which means that we have n equals 1. So there's our first ring. And then we have n equals 2. So these quantum numbers, remember the first 3 quantum numbers, n, l, and m sub l, describe the orbital, or where the electron might be hanging out in the atom. And the spin quantum number, m sub s, just describes its spin, right? +1/2, -1/2. But if you look on the periodic table, you can actually imagine that the n values are the numbers that go down the periodic table that describe the rows, right? So n equals 1, n equals 2, n equals 3. The groups are the columns, the up and down columns, right? So for main group elements, hydrogen's in group 1, right? They put helium over in group 8, mostly just because it has a full outer shell. But you'll notice things like magnesium and calcium hanging out in the second group, right? Carbon's over in group 4, nitrogen's in group 5, whatever. An interesting thing, a trend anyways, on the periodic table is that this effective nuclear charge matches up with the group that the element is in for main group elements. So for lithium, this effective nuclear charge will be our nuclear charge, so that's going to be 3, minus the core electrons or the shielding electrons. So imagine you are this electron. And by the way, the outermost electrons for a main group element are going to be the valence electrons. So this right here, outermost electron, is otherwise known as a valence electron. Why do we care? Well, because the valence electrons, the ones that are farthest away from that positive charge, those are the most loosely held by the atom. The closer these negatively charged particles get to the center of positive charge, right, the more tightly they're held by the atom. So the core electrons, which will be these right here, so these are core electrons, and those are what we call our shielding electrons. They are shielding the outermost electron from the center of positive charge. Those core electrons are held a little bit more tightly by the atom because they're closer, right, in proximity to the center of positive charge. So the Coulombic force of attraction between those electrons and the nucleus is going to be greater. The outermost electron, the valence electron, are where we focus in chemistry because those are the electrons that we're going to use for bonding. They are most loosely held by the atom. So they are the most likely, right? So statistically speaking, they are the most likely to be involved in either being shared with another atom or just completely donated, right, to another atom. So when we talk about the shielding electrons or the core electrons, we're saying that nuclear charge is going to be shielded from the outermost electron by those two. And notice how lithium also has an effective nuclear charge or a core charge of +1. Notice how lithium is also hanging out in the first group. All of your group 1 elements will have an effective nuclear charge of +1. They all, since they're main group elements, also typically form a +1 charge. So they form that +1 cation. Group 2 elements will form a +2, right? Group 3, +3. Then you move over into the other side of the periodic table, starting with group 4, and we get into elements that have what's called a higher electronegativity. So electronegativity basically describes, so we often sort of abbreviate this EN. So this is electronegativity. So in some Gen Chem classes, instructors will say this is the affinity an atom has for electrons. And that's not necessarily untrue. It's just a little misleading because there's another trend in the periodic table called the electron affinity. They are not the same thing. Electronegativity basically kind of describes how tightly an atom is going to hang on to its own valence electrons. And it also kind of describes the affinity, I guess is a bad word to use, but how interested that atom might be in somebody else's valence electrons when that atom is in a bonding situation. So this is how tightly or loosely an atom hangs on to its valence electrons. You can also kind of think of it like how attracted an atom is to another atom's valence electrons. So, and by the way, this is not something that you can actually dip into a flask and measure. This is more like a behavior that we notice. And the trend for electronegativity is that it increases from left to right and up on the periodic table. So in other words, for the bonding elements, cesium has the lowest electronegativity and fluorine has the highest. For our bonding elements. So what that means for us is that fluorine has a tendency to hang on to its own valence electrons more fiercely than any other atom, bonding atom on the table. It also has the greatest attraction for somebody else's electrons. So if you were to bond fluorine with say like a carbon or a hydrogen or something less electronegative than itself, which anything would be, then in that bond, if those electrons are being shared between the two atoms, the fluorine is hogging them, right? And so the electron density is greatest over by the fluorine. Cesium has the lowest electronegativity, so that outermost electron is so loosely held by the cesium atom that it typically just donates it to somebody else. So there is no sharing involved. So cesium being a metal, this is another trend on the periodic table. We notice that the metals, typically main group metals, have lower negativities, or at least I should say the group 1 and 2 metals have the lower electronegativities, and they have a tendency to just donate them to nonmetals. The nonmetals have higher electronegativities, so they have a tendency to accept them. So if you're going to be forming an ionic bond versus a covalent bond, meaning you're going to make a salt, we're going to have one atom completely donate its valence electrons to another atom. It's going to be the one that has the lower electronegativity. It's more loosely hanging on to its own valence electrons and not particularly interested in picking up anybody else's. So we notice that group 1 and group 2 elements typically form +1 and +2 cations. And then starting over in group 4 with carbon, we're talking our main group elements, the transition elements are a little different. Their valence electrons also include their outermost d electrons, which are sort of one shell in. In organic chemistry, we don't really focus too much on the transition metals, and that can be kind of nice for some people, right? We typically start talking in period 2 with carbon, and we focus mostly on carbon, nitrogen, oxygen, and fluorine, also hydrogen, and then sometimes phosphorus and sulfur. And then that's pretty much it, right? And if we're going to be making salts, we typically talk about things like sodium, potassium, magnesium, and calcium. Not like anything else doesn't exist. It's just that in organic chemistry, we have a focus on those particular elements. So I just wanted to give kind of like a general overview of Gen Chem and just kind of bring us all back to the same page, or at least start off from the same point in terms of what you should probably remember. In terms of bonding, this electronegativity is just going to come back to haunt us over and over again when we start talking about things like polarity. So for example, like when I mentioned, hydrogen bonding to fluorine, that's going to be a polar covalent bond, right? So the electrons in bond are going to be shared between the hydrogen and the fluorine, but they're not going to be shared evenly. And so you have to look back at like the electronegativity of the atoms involved. Fluorine has the greatest electronegativity of the bonding elements. It's going to be hogging the electron density in that bond. And so you end up with what we call a polarity, a partial positive charge on the hydrogen, a partial negative charge on the fluorine. And that affects the way that those particular molecules behave, right? The acidity of the hydrogen, or in other words, like if you were to attack that molecule, right, with something else, say with another pair of electrons from something else, like where is it going to get attacked? So when we say, hey, think back to Gen Chem, this is what we're kind of going back to here. And again, electronegativity is not something that you can just directly measure. It's more of like a behavior. How is this thing behaving when it's hanging out with another atom? How is fluorine behaving when it's hanging out with another atom? Oxygen is more electronegative than carbon, but it's less electronegative than fluorine, those kind of things. So it's just sort of like, and we use numbers. There are numbers like a little scale to sort of give you an idea of sort of like who's more electronegative than who else kind of a thing. And so you might see things like 2.0 is associated with hydrogen, 4.0 associated with fluorine. It doesn't mean that anybody was like, measuring something with like a meter or something like that. It just means like, hey, we're just assigning numbers so you can sort of wrap your mind around like where on a scale these things might fall. Another piece to these electronic structures would be electron configurations. Remember those? So the electron configuration can be helpful because it can help us sort of identify the valence electrons, which ones are most likely to be ejected from the atom, right, or used in bonding. So electron configurations. Now, you can write these all out. So you're, writing out every single electron in the atom, or you could do it a little bit more like the shell model and use the shorthand notation, meaning if I were to take something like carbon, you look on the periodic table and you see carbon over in group 4, but it's in the second period. And we remember from Gen Chem that we're going to be filling our electrons from the inside of the atom out, meaning we're going to start with the lowest potential energy spots. The lowest potential energy spots, or the best seats in the house, are going to go for the electrons sitting closest to the nucleus, right? So we start with our 1s orbital, and we're going to put 2 electrons in there. We're completely filling that particular subshell. So by the way, we just like revisit what this actually means here in case it's been a while for someone. This big number right here is the N value. That's your shell. Or in other words, your energy level. S is a letter that describes the shape of the orbital. So this is your L quantum number, right? So this is our subshell. And this little 2 up here is the number of electrons that are hanging out in that particular orbital. So the 1s orbital, right, has 2 electrons in it. If you're looking on the periodic table, now you remember from Gen Chem that you can only put 2 electrons in one orbital, right? The Pauli exclusion principle tells us that no 2 electrons can occupy the same quantum space. So we've got, and I can underneath here, in terms of energy, you can write this differently if you like, and say, here's the nucleus down here. That 1s orbital is closest to the nucleus. So if you're imagining the shell model, right, with the protons in the center and then that first ring, that's our 1s orbital. We have 2 electrons, spin up and spin down. And then that's it, right? There's only one s orbital there. So now we have to move out to the next ring, which is going to be 2s. Move this thing out of the way. And write this up here. Okay. We're going to put 2 electrons in here. So if you're following carbon, in order to, you're taking a little journey, right, across this periodic table, and you're stepping through the first 2 boxes on the left-hand side in the second period, right, basically. So each box, you get a proton, each box, you get an electron. We have our 2s orbital. There are 2 electrons hanging out in this particular orbital, right? Can't have a third or a fourth because you can only have spin up and spin down. Once we have that taken care of, we have to move into another orbital, and we're going to fill one at a time. So that's Hund's rule, right? We're still in the second period, but now we're in the P subshell. And if you're looking at carbon, you notice that when you get over to the right-hand side of the periodic table, in other words, we call it the P block, you're going to step into boron's box and then carbon's box, right? So you get 2 more electrons. If you look at the atomic number in the box with the big C, right, you see a 6 there. There are 6 protons. That's what that atomic number tells you. And for a neutral element, you also have the same number of electrons. So for a neutral atom of carbon, we have 6 protons and we have 6 electrons. This electron configuration tells you all of the electrons that are actually in the atom, right? Or if you wanted to do an ion, you could do that too. It's going to tell you the total number of electrons, right? In the energy level diagram, we notice that our 2p subshell, right, or the 2p orbitals are just a little bit farther away from the nucleus than the electrons hanging out in the 2s. And how do we know that? Photoelectron spectroscopy, right? So you can actually measure the amount of energy that was necessary to knock those electrons out of their position. The farther away they are from the nucleus, the more loosely they are held by the atom, the easier, or in other words, the less energy necessary to knock them out, which is kind of how we imagine that we have this sub-level splitting. We're going to fill each orbital with 1 electron at a time. Everybody gets 1 helping before they get 2, right? So single electrons go into orbitals first before they start to pair up with the same spin. So we just arbitrarily begin with a positive 1/2 spin. You could arbitrarily begin with a negative 1/2 spin. Really, at the end of the day, it's all just a cartoon model, right? For us to try to understand this atomic landscape. For us, what this means, though, is that if you wanted to say, hey, I don't really care about all the electrons in carbon. I want to kind of focus on what electrons are going to be available for bonding. And then you want to be like, okay, well, if I imagine that the electrons that are hanging out closer to the nucleus are going to be less available for bonding because they are, again, more attracted to the nucleus, right? The center of positive charge. Then of the valence electrons that are available, 2 of those electrons are probably going to be most available, right? The ones that are farther from the nucleus. We have a way to sort of encapsulate the core electrons for the main group elements. What we do is we say, we're going to take the core electrons and we're going to put them in brackets, and we're going to use the elemental symbol for the noble gas associated with those core electrons, or the last time you had a complete shell, basically, for the atom. The last time carbon had a complete shell, it was isoelectronic with helium. Iso means same. Electronic means electrons, right? So 1s2, in other words, is the electron configuration for helium. Those are the core electrons for carbon. So we put those in brackets, and then the valence electrons, or whatever electrons are left, the outermost electrons, are outside in order of their potential energy. So increasing potential energy from left to right. These are going to be the valence electrons for carbon. Notice how carbon has 4 valence electrons. Notice how carbon is also in group 4. So another thing about the periodic table for the main group elements, and by main group, I mean groups 1, 2, and then groups 3 through 8. So not the transition elements, right? So for the main group elements, the number of valence electrons are going to be the same number as their group number. So the periodic table tells you kind of a lot of stuff, useful stuff. Let's do an ion. Let's do just sodium. I'll do just sodium, and then we'll ionize it because I want to show you something. So again, we're going to start with our lowest potential energy spots, best seats in the house, closest to the nucleus, 1s2, then 2s2. For sodium, we completely fill the second period, so 2p6, and then 3s1. So now, if you're staring at this, you're like, that's sodium, neutral sodium. It has 2, 4, 10, 11 electrons. If you look at sodium, it has an 11 in its box, right? So it's got 11 protons. Neutral sodium also has 11 electrons. So you can always check your electron configuration to be like, hey, did I mess up an electron somewhere? Like, am I missing something? Count them out, those little superscripts. They should match up with the atomic number if you have a neutral element. I can also write this shorthand notation if I like. So I can be like, all right, well, these right here are going to be the core electrons. Like, for example, when's the last time sodium had a complete shell, right? So these are the core electrons. And those core electrons, or in other words, that particular group there, that electron configuration, is isoelectronic with neon. So we stick all our core electrons in a little box, these little brackets here, and who's left? The outermost electron. It's 3s1. This right here is the valence electron for sodium. So if I'm going to ionize this now, one thing that you want to make sure that you think about is that sodium is a metal over in group 1. It has a pretty low electronegativity. So in bonding land, it has a tendency to give up an electron instead of accepting one. So it's going to donate its valence electron. It only has one. So it has a tendency to, don't mind my cat, it has a tendency to give up that single electron and form the +1 cation. If you look at where sodium is, it's in group 1, right? Another trend on the periodic table is that the group 1 elements have a tendency to form +1 cations. So if I ionize this electron goes when sodium is ionized. So what that means is if we take that electron away, we don't change the number of protons, right, in the nucleus. We're just changing the number of electrons hanging out outside the nucleus. Now we're missing an electron, right? Electrons have a -1 charge. So we're going to take on a +1 charge when we eject that electron. So sodium +1, the cation, has an electron configuration of 1s2, 2s2, 2p6. That 3s1 electron has been knocked out, right? So we hit that thing with a certain amount of energy, whatever energy was basically holding that electron in that spot, and we ionize the sodium. You can write the shorthand electron configuration for this, but you need to be careful because the core electrons are different now. This might be a nice spot to talk about why sodium does not typically exist in the +2 oxidation state. Like theoretically, you could make sodium +11, right? But out in nature, we find it always hanging out in the +1 oxidation state. And why is that? So now if you look at this electron configuration, you notice that the core electrons, the innermost electrons, are here. And the valence electrons are now here. So if you were going to make sodium +2, you'd have to knock out one of those valence electrons. The core electrons are isoelectronic with helium. And now the valence electrons are these. So it might be a good time to bring back the shell model just quickly, especially for sodium, and say, hey, what's the deal here with sodium forming +1 cations, but not +2? Don't mind my awesome rings. So we're going to fill this out. We've got 2 electrons in the n = 1 energy level. We move out to n = 2. We've got 1, 2, 3, 4, 5, 6, 7, 8, right? And then in n = 3, we have 1 electron. So this is regular old sodium. If we lose an electron, it's going to be this outermost electron. It's the farthest away from the nucleus. It's the most loosely held by the atom. So we're knocking that out. -1 electron. And we have +11, because that doesn't change. We have n = 1, n = 2, right? I'll draw the ring here, but there's no electron after we've ionized. And if you remember from Gen Chem, and I'm drawing these terribly because I've had a lot of coffee, but these particular rings get closer together the farther you get away from the nucleus, right? So the n = 3 ring might be a little closer to n = 2 than that. But what you're left with here that's 8, right? Yeah. This is sodium +1. So we've ionized the sodium, right? We now have different number of core electrons than we did before, right? So when we had that one valence electron in the third energy level, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So if you're going to be figuring out the core charge or the effective nuclear charge, you could just say, I'm going to look at the periodic table and it's in group 1, so it's got to be +1. Or you could be like, here's the nuclear charge of 11. I'm going to subtract the 10 core electrons. And there's my +1 effective nuclear charge or core charge. So +1, right? We're going to knock out that outermost electron, and then we want to ionize the sodium again to make +2. So what's the likelihood of this? Well, now all of a sudden, my valence electrons are these. So if I want to make sodium +2, one of these has to go. What happened to the effective nuclear charge? I still have 11 protons in the nucleus, but now I only have 2 core electrons, the inner electrons, right? So now all of a sudden my effective nuclear charge went up to +9. Now, it doesn't take a lot to imagine that it's much easier to eject an electron from an atom with a core charge or an effective nuclear charge of +1. Like, for example, the energy holding that electron in its spot, right? We can crudely imagine is +1, right? In terms of like a pull. But now, after we've ionized it and taken away 1 electron from sodium, the core charge or the effective nuclear charge jumps to +9. It's going to take a lot more energy to remove one of those 8 electrons, right, in that second energy level. They're closer to the nucleus and they're only being shielded, theoretically, by 2 of those inner electrons. So that's sort of the story that we tell ourselves. At the end of the day, the data is what it is. Sodium exists primarily or always in the +1 oxidation state. Why doesn't it exist in the +2 oxidation state? Probably because it's going to take too much energy to take away one of those new valence electrons. Let's see. So I think I'm gonna end this particular video here. In the next video, what I'd like to do is focus on bonding. So now that we have discussed the electronic structure of an atom, let's use that information to talk about the 2 different types of bonding. There are 3 different types of bonding. We'll casually mention metallic bonding, but in an organic chemistry class, we're going to be mostly focused on ionic and covalent bonding. And ionic bonding is where we're going to completely donate electrons from one species to another. And there'll be this electrostatic force of attraction between the positively charged species, the thing that donated the electrons, and the negatively charged species, the thing that accepted them. In covalent bonding, we've got sharing of electrons. So if you've got 2 atoms that have closer or more similar electronegativities, then you have a tendency where these atoms are going to share electrons. They can share them evenly or equally. So if you have 2 of the same atom bonded to each other, and you have what's called a polar or non-polar, covalent bond. If you've got 2 atoms with different electronegativities, but they're not, like, the difference is not so huge that it becomes ionic, but it's a good amount all the same, then we have what's called a polar covalent bond. So we'll talk about those differences in the next video.